you can take over in a second. Welcome everyone to our Monday seminar series. We are very lucky that Professor Cristiano Collettini is going to talk to us today. The formal part of the introduction was done by email, so please forgive me if we don't recapitulate all of the honors that Cristiano has attained in his background, but you'll see more about that as we go. The seminar series has been going on for a while now, I guess coming up on some part of the end of 3 years. And we have typically been quite informal. I'd ask people to turn off their mic, leave their camera, do what they want. Of course, you know, Cristiano is not too far down the hall from many of us here in Sapienza, so there are a few of us around. And but it is hard to give a talk by Zoom, so please feel free to interrupt with points of clarification. And then at the end, we have usually a nice extended time for questions and discussion. And with that, I will turn things over to Cristiano. Thank you very much, Cristiano.
Okay, thank you, Chris. And yeah, today I would like to talk about on-fault versus distributed seismicity and see the role played by rock and fault rheology. And what I'm going to present you today is the result of my collaboration with Massimiliano Barchi from Perugia University, who was my PhD advisor, Nicola De Paola from Durham University, and my colleagues in Sapienza, Fabio Trippetta and Elisa Tinti. So I will start, I will use the 2016 Central Italy seismic sequence to discuss about on-fault seismicity. And for on-fault seismicity, I mean this seismicity that is occurring along the earthquake fault. So the seismicity associated to the main shock of the seismic sequence, seismicity that is occurring on fault structures like this one, affected by cataclastic process with grain size reduction and localization. And these faults are associated to an elasto-frictional rheology promoting a stick slip behavior. So this is something quite common for faults belonging to the seismogenic regime. Then I would like to discuss about this seismicity that does not show any specific alignment that can be diagnostic of a major fault. And we are going to call this distributed seismicity. And since in the area where this Central Italy seismic sequence is occurring, there are seismic reflection profiles, we can constrain the lithology where this seismicity is occurring. And this lithology is the Triassic evaporites, a lithology that is dominated by the ductile behavior of the anhydrites. And so we will associate this distributed seismicity to the ductile behavior of the Triassic evaporites. And I will also show you that on-fault versus distributed seismicity show also differences in the earthquake frequency magnitude distribution. Okay, so this is the main message I would like to deliver you today. And now I would like to set the scene for these topics. So in the upper 10-15 kilometers of the continental crust, the base of the background seismicity defines the brittle ductile transition. That is a transition where faulting occurs along localized zone of deformation, mostly characterized by an elasto-frictional rheology. Below the brittle ductile transition, deformation is distributed on a thick myelonitic shear zone where the deformation is ductile. And within the seismogenic regime, strain localization along faults produce a structure that is characterized by a fault core where most of the slip occurs, surrounded by a set of subsidiary faults, small faults, fractures that is generally defined as the damaged zone. And the total fault zone thickness, including the core and the damaged zone, scales with fault displacement. But for displacement larger than 2-3 kilometers, it levels at a couple of hundred of meters. And the geometry of active faults at depth is mainly illuminated by aftershock distribution that define a zone of high seismic activity close to the earthquake fault. And this zone of enhanced seismicity includes and sometimes extends beyond the fault zone structure as being defined by structural geology. So this thickness of the fault zone structure, and this zone that extends beyond the fault zone structure is being defined as a zone of shear deformation. In terms of earthquake mechanism, the zone of shear deformation is characterized by an elasto-frictional rheology because it is controlled by the frictional properties of the fault and the elastic properties of the fault loading medium. During tectonic loading, when the shear resistance is overcome for specific pre-frictional properties of the fault, a frictional instability occurs, and so a main shock nucleate. Following the main shock, aftershock relax stress concentration, and they usually occurs around the activated fault, like for example, in this earthquake occurring in central Italy in 2009. So within the seismogenic regime, high resolution earthquake locations have been used to characterize the geometry of the active faults. For example, along the creeping segment of the Sant'Andreas fault, parallel fault segments have been illuminated by microseismicity, or during the 2019 ridge-crest seismic sequence, orthogonal faulting has been documented with some branching close to the earthquake rupture tip, or in extensional environment, parallel fault segments with antithetic structures, some dilational jogs, branching at shallow crustal levels have been documented by aftershock distribution, and extensional detachment cutting the entire seismogenic layer from shallow crustal level down to the bottom of the seismogenic layer has been documented by microseismicity distribution. However, within the seismogenic layer, seismicity is not exclusive of the major structure. For example, here along the San Jacinto fault zone, most of these low magnitude seismicity is occurring on a zone that is several kilometers wide at seismogenic depths. Or during the ridge crescent, the aftershock define a zone of deformation that is about up to 10 kilometers wide around the earthquake hypocenters. Or during this swarm sequence, these fault fracture mesh that is up to 2 kilometers wide has been documented by earthquake location, magnitude, and focal mechanisms. And this fault fracture mesh is similar to the models of fault fracture melt built on the grounds of geological observations. And in some fluid pressure stimulation, a broad network of fractures has been highlighted by microseismicity distribution without any specific seismicity alignment along a major fault. To explain distributed seismicity, several mechanisms have been proposed, and they include and are not limited to fault step over or fault branching, deformation accommodated by many small faults, like for example, the fault fracture mesh that has been documented during the swarm activity along a fault in California, or loading from an ongoing ductile deformation. And overall, these studies presented in this introduction emphasize that a fault structure that can be constrained by field geology or by precise earthquake location, and rheology. So the fault rheology, mostly characterized by the frictional properties of the rocks in the lab, or rock rheology, for example, that we can constrain by triaxial tests, always in the lab. So fault structure and rheology play a primary role in controlling the distribution of the seismicity. But usually all these ingredients are difficult to be constrained over the entire seismogenic depth range. But this is not the case of the northern Apennines of Italy, where in the 80s, a broad network of seismic reflection profiles, together with deep boreholes, have been acquired for oil exploration. So the Italian oil company didn't succeed in finding oil in the Apennines, but these data became fundamental for constraining the geology of the rock present within the seismogenic layer in the Apennines. And also in the same area, we can study outcrops of exhumed faults, showing the deformation process that play a key role at depth in the seismicity occurrence, in seismicity development. So in this talk, I'm going to try to explain differences between on-fault and distributed seismicity due to differences in rock and fault rheology. And to do that, I will use the 2016 Central Italy seismic sequence that started at the end of August 2016 with this Amatrice earthquake that was a magnitude 6, and it was followed 2 months later by the Norcia main shock, a magnitude 6.5. 4 days before the Norcia, this earthquake, Viso earthquake, a magnitude 5.9 occurred in this area. And just to give you the flavor of the geological evolution of the area was affected by late Miocene, early Pliocene, Apenninic compressional phase with north-south trending anticlines associated with north-south trending west-dipping thrusts. And this compressional phase was superimposed by late Pliocene quaternary extension occurring on northwest-southeast trending normal faults. And in this area, we use this seismic reflection profile to constrain the geometry of the rocks within the seismogenic layer. For example, starting from surface geology, where we see this anticline can be followed at depth in seismic reflection profiles. This is the reflector, a reflector within the carbonates of the Apennines, and this is the reflector of the top of the Triassic evaporites. Here we have got another anticline that can be followed here with the reflector within the carbonates, the top of the Triassic evaporites. And here there are the reflectors that are interpreted as the philitic basement, the top of the philitic basement. Here are at 3.2 seconds in two-way time, and here they are at 2.7 seconds in two-way time. And this is the Montevettore normal fault that was reactivated during both the Amatrice, this co-seismic slip at the surface, and Norcia, this co-seismic slip at the surface. So building on these seismic reflection profiles integrated with surface geology, we have reconstructed this geological cross-section that is oriented perpendicular to the strike of the activated fault and passes through the main shock. The geology of the area of the seismogenic layer can be schematically summarized as follows. At depth above 6 kilometers, we have got the carbonates and the Triassic evaporites, From 6 to 9 kilometers, we have got the Triassic evaporites, and below 9 kilometers, there are the rock of the phyllitic basement. Okay, now let's present a bit the seismicity of the 2016 seismic sequence. And to do that, we use the catalog published by Ton et al. That is made of 900,000 earthquakes detected with a machine learning algorithm, FaceNet, and located with a double different method. In the section I'm going to show you today, we are plotting the seismicity occurring within 1 kilometer from the cross section. So here there's the seismicity occurring in the 2 months before the Norcia main shock. We can see that the seismicity highlights the future rupture plane. There are some clusters here that we define C2 and C3, and here down deep in the hanging wall block of the main shock rupture plane, there's only a few seismicity. This is the seismicity in the 40 days after the Norcia main shock. There's still seismicity illuminating the earthquake rupture plane, but we see abundant and distributed seismicity in this area down deep in the hanging wall of the earthquake rupture plane. So we call this DHWS, down deep hanging wall seismicity. The seismicity in cluster C2 and C3 turn off, and there are other clusters that are activated following the Norcia main shock. What we think is interesting is that a great number of these distributed seismicity is occurring at depth within volumes where the seismic reflection profiles constrain the presence of the Triassic evaporites. So in our interpretation, this is a distributed seismicity that is mainly triggered by the enhanced ductile behavior of the Triassic evaporites following the main shock, following the stress changes produced by the main shock. But before going into the details of our interpretation, I think it is important to present other interpretation for this thick basal seismicity located below the main shock hypocenters. So from the subhorizontal geometry and from the extensional focal mechanisms, this basal seismicity has been interpreted as an extensional shear zone that in some places is fragmented. From the imbrication of these thick seismicity bands, reactivation of truss inherited from the previously developed compressional phase has been proposed. In our interpretation, these thick zones of microseismicity do not highlight the reactivation of a major fault at depth, either an extensional detachment or a compressional thrust, but they are instead volumes of distributed microseismicity occurring within the Triassic evaporites. And these seismicity bands within the Triassic evaporites are constrained at depth by the top of the basement that is affected by compressional steps, and it acts as a seismicity cutoff. So in our interpretation in this area, the seismicity cutoff is frictionally controlled. And so now only by using this slide, I'm gonna try to better constrain this frictionally controlled seismicity cutoff. The details can be found in this manuscript. So here in the active area of the Apennines, the light blue, deep borehole and seismic reflection profiles constrain the depth of the basement that represent a sort of a seismicity cutoff. Whereas here in Tuscany and in the Tyrrhenian Island, outcrop of rocks representing the philitic basement are exposed. We collected these rocks, we did some frictional tests, and they are rich in phyllosilicates, so friction is quite low, 0.2, 0.3. But what is relevant for being a good seismicity cutoff is the velocity dependence of friction of these rocks, showing a rate strengthening behavior that becomes more and more rate strengthening with increasing sliding velocity. So in our interpretation, the seismicity cutoff of the Apennines is frictionally controlled, and in particular is dictated by the velocity strengthening behavior of these phyllosilicate rich rocks. Above the basement, these thick zones of seismicity represent distributed seismicity within the Triassic evaporite, triggered by the enhanced post-main shock ductile brittle behavior of the Triassic evaporites. So now I would like to better constrain the rheology of this lithology. So these Triassic evaporites have got a bimodal style of deformation. Along the major normal faults of the area with displacement of several hundred of meters, the fault zone structure is brittle. So the typical fault zone structures of faults within the seismogenic regime, and away from the major structures, the deformation is ductile, is pervasive. So to better constrain the rheology of on-fault deformation, here we are looking at one fault exhumed from 3-5 kilometers. So here in the field, we can observe the deformation process responsible of this seismicity at depth in the active area of the Apennine. And the deformation of this fault is cataclastic with grain size reduction and localization along principal slipping zones. And this localization that we observe in the field is the one that during friction tests in the lab on these fault rocks, this localization promotes a transition from a rate strengthening to a rate weakening behavior, promoting this stick slip behavior, so promoting these frictional instabilities. Away from the major normal faults of the area, the deformation of these Triassic evaporites is ductile. So to better constrain this rheology, just I want to give you just some information about the stratigraphy of this lithology that is made of interbeds of dolostone, the heavy gray, and anhydrites, the light rocks, the white rocks. And the thickness of this lithology is up to 4 kilometers. For example, here, this borehole document 3 kilometers of this lithology, at least 3 kilometers. And at the core of the anticlines, or where thrust faulting produce a doubling of the seismic sequence of this lithology, the seismic profiles show a thickness that can be up to 4 kilometers. And the deformation is pervasive and represented by folding, like here, boudinage of the more competent lithologies represented by the dolostones. Folding of the anhydrites layers produce fractures with domino-like structures in the dolostone layer, and rotated folds that detach into gypsum anhydrite rocks emphasize the interplay between brittle and ductile deformation during the deformation of these Triassic evaporites. Brittle deformation is widespread within the dolostone, as you can see here, by subvertical hydrofracture, testifying fluid pressure builds up and release during the extensional deformation phase of the Apennines, And small displacement, gently dipping, normal faults are widespread within this lithology. But the main deformation is ductile. And we have better constrained this deformation that here we can infer from the field using laboratory experiments. So we have collected rock samples of anhydrites from the deep borehole of the Apennines, and we have conducted triaxial deformation tests on these rocks. So in this experiment, we fixed a confining pressure at 100 MPa, and then we did a test at different values of fluid pressure, from 60 to 90 MPa of fluid pressure. So we move from suprahydrostatic to near lithostatic fluid pressure value. And even if these experiments were run at room temperature, the deformation is in most of the tests that we have done is ductile and associated to pervasive cataclastic flow within the deforming sample. And only for fluid pressure approaching lithostatic value, we observe localized deformation along a fault with gouge and stress drop. But the main deformation is ductile, even if this test has been run at room temperature. And the ductile deformation of the Triassic evaporites promotes also a very low permeability for this lithology, both static and dynamic permeability. So here, the static values are below 10 to the power of minus 19 meters square, even for high value of fluid pressure or for low value of the effective normal stress. So for those who are not very familiar with permeability values, we can set a value of 10 to the power of minus 17 as a threshold. Above 10 to the power of minus 17, fluid flow is allowed within the seismogenic layer. For values below 10 to the power of minus 17, the rocks start to act as a sealing horizon that traps fluids. And the Triassic evaporites show the permeability well below 10 to the power of minus 17. So we are between 19 and 21. And these low value of permeability are maintained also during deformation. So because the deformation is pervasive, because there's a lot of tortuosity for fluids, even during accumulating strain, the permeability is maintained below 10 to the power of minus 19. And so this sealing attitude of the Triassic evaporites is in agreement with fluid overpressure trapped within this lithology and documented in the borehole of the Apennines. For example, here in this deep borehole at 4.7 kilometers, a fluid overpressure of 100 MPa has been documented, corresponding to a near lithostatic fluid pressure, pore fluid factor, that is the ratio of fluid pressure over the lithostatic load equal to, or at least equal to 0.9. And here in this borehole, we can see how fluid overpressure can be compartmentalized within the Triassic evaporite. So these are the pockets of fluid overpressure that are stored within the dolostone, that are fractured and that are sealed on the top by the Triassic, by the anhydrites, because of these low permeability values. So I started from this picture and I have tried so far to provide more constraints for this interpretation for the elasto-frictional rheology along on-fault deformation and for the ductile rheology of the Triassic evaporite associated to this distributed deformation. We have also tried to search for further differences in on-fault versus distributed seismicity from the earthquake frequency magnitude distributions.
Cristiano,
See?
it's Chris.
Yeah.
Can you tell us a little, the scale at the lower left there in panel D, how does that fit into what we look at when we look at the seismicity?
Yeah, here, yeah, I think this is one of the larger field outcrop I have seen during field trips. So here it's about 300 meters.
Yeah.
From left to right, this is about 300 meters.
Yeah, okay, thanks.
So it's just, so here it's 2 kilometers. So it's just a rectangle here. But yeah, in the field, it is very, very difficult to find exposures larger than something like that.
Yeah, right. Yeah, and it's always a question of like, so the biggest earthquakes that are occurring in this microseismicity, I mean, I know you're coming to that, but yeah, it's interesting to think of the tiny things that are happening in here are maybe not so hard to understand because there are parts of this that are brittle, even though if the overall structure is ductile, right?
Yeah.
Short question, Georg here. What is the thickness of the evaporites in that area?
So so since the deformation is a ductile, the thickness can change. So yeah, so on seismic reflection profiles, the standard thickness, the standard stratigraphic thickness is about 2 kilometers. But at the core of the anticlines, or where crust produce a doubling of the sequence, the thickness can be up to 4 kilometers. And for example, in the Monte Civitello borehole, it has been drilled 3 kilometers of Triassic evaporite in continuity, and can be even larger because they started at 3 kilometers with the Triassic evaporites, and at 6 kilometers they stopped, but they were still within the Triassic evaporites.
Thank you.
So from 2 to 4 kilometers.
Mm-hmm.
Okay, so we have seen, or we interpret these differences between on-fault versus distributed seismicity as differences in rheology within the seismogenic layer. And we have searched for further differences between on-fault versus distributed seismicity from earthquakes frequency magnitude distributions. And to do that, we started from the Gutenberg-Richter law, and we tried to quantify the B values in the Gutenberg-Richter law that quantifies the proportion of small to large magnitude events. And we have evaluated the B value for on-fault seismicity by selecting the earthquakes occurring at distance less than 0.5 kilometers from the main shock fault plane, so this seismicity. And then we evaluate the B value for distributed seismicity. And for that, we constrain the B value for this seismicity, the down deep hanging wall seismicity, and the seismicity that is occurring within these clusters, C1, C2, and C3. So these are the results. The B value for the different volume of the seismogenic layer that we have analyzed are different and systematically lower in on-fault versus distributed seismicity. For example, this is before Visso-Norcia main shock, and on-fault is 1.17, distributed in this area is 1.61, and this is for the entire sequence, 1.34 for the fault, and 1.54 for the down deep hanging wall seismicity. And this is the seismicity on the B value on the clusters that is in the range 1.66, 1.81. So these high values for this distributed seismicity suggest that the Triassic evaporites are prone to activate a large number of distributed faults and fractures with limited size. And in addition, if we look at the seismicity evolution within these clusters, we observe that the seismicity rates in this cluster evolve in time with this increase, decrease, increase, decrease, increase, decrease. So this seismicity rate does not follow an Omori type decay. And also the magnitude are homogeneously distributed during this time of the cluster activity. So we interpret this seismicity as a swarm-like activity. And in our interpretation, this swarm-like seismicity is due to both the ductile behavior of the Triassic evaporite together with fluid overpressure that can be easily trapped within this lithology. And these evidences for fluid overpressure derive from field observation, like the hydrofracture system documented within the Triassic evaporites, the compartmentalized fluid overpressure in a deep borehole within the active region of the Apennines, and this high VPVS value interpreted as an overpressurized volume where these clusters C2 and C3 are occurring. So our conclusions: on-fault seismicity occurs along the major normal fault of the area that are affected by cataclastic process with grain size reduction and localization. And these structures are characterized by an elasto-frictional rheology promoting a stick-slip behavior. And this seismicity, the seismicity on fault, is associated to relatively low B values. Distributed seismicity is mainly due to the enhanced ductile behavior of the evaporites following the main shock, triggering fracturing and faulting within the dolostones, failure within the anhydrites, and reactivation of small normal faults within the Triassic evaporites. And this distributed deformation shows higher B values in the range of 1.44, 54, 80, 1.81. So some implication: ductile brittle cluster deformation can cause distributed microseismicity, which obeys to different scaling laws than on-fault seismicity, and lithological heterogeneity strongly or can strongly influence seismicity distributions and seismicity rates, and need to be considered to explain the complexities of some seismic sequence. So to further explore the role of lithology in earthquake frequency magnitude distribution, we have selected this sort of a stratigraphic section on this geological cross-section that we built on building on these seismic reflection profiles. And then we have selected the earthquakes occurring within the carbonates. So the earthquakes occurring here and here within the carbonates with brittle dominated deformation along small displacement faults. The earthquakes occurring within the Triassic evaporites with a ductile brittle dominated deformation plus compartmentalized fluid pressure resulting in a strong stress heterogeneities, and the seismicity occurring within the phyllitic basement that is rate strengthening, and that these phyllosilicates surround more competent quartz-rich lithologies. So we selected the earthquakes for the carbonates. So and the Triassic evaporites and the phyllitic basement. And to do that, from the cross section, we selected a long strike distance of ±5 kilometers. And then in the down deep direction, we have chosen some dimension to stay within the lithologies, and the depth, we choose the depth to stay within the carbonates, the Triassic evaporites, and the phyllitic basement. So these are the selected earthquakes: upper carbonates, upper Triassic evaporites, lower carbonates, lower Triassic evaporites, and phyllitic basement. So from this earthquake catalog, we reconstructed the B values. And we see that there's a lithological control on the B values. The carbonates are in the range 1.24, 1.37. The Triassic evaporites are in the range 1.56, 1.63, and the basement shows a B value around 1.43. And also the seismicity rate changes through time. So the carbonates and the basement show an Omori type decay following the main shocks, whereas the Triassic evaporites show an increase and decrease through time that represent a more swarm-like activity. Like, for example, this cluster that was activated in the middle of October, or this cluster here that was activated from the middle of December and early January 2017. So to summarize, on-fault seismicity and the seismicity within the carbonates show B values that is 1.3 plus or minus 0.15, and we associate to an elasto-frictional dominated deformation on fault and within the carbonates. The Triassic evaporites show a B value that is significantly higher, 1.6 plus minus 0.15, and is associated to a ductile brittle dominated deformation plus fluid pressure development, fluid flow within this lithology that show this swarm-like activity. And the basement is characterized by a B value that is 1.4 plus or minus 0.05. It's quite stable, the B value within the basement. And we associate to the rate strengthening behavior of the phyllosilicate plus brittle process occurring within the quartz rich lenses. And so these studies to emphasize that lithological heterogeneity strongly influence seismicity distributions and seismicity rates, and need to be considered to better explain the complexities of the seismic sequences. Thank you.
I'll invite everyone to join me in thanking Cristiano. Fabulous talk. Please go ahead and turn on your microphone if you'd like. Yeah, really interesting, Cristiano. Okay, beautiful. I don't have to explain too much, but I will anyway. If you're joining us for the first time, it's useful to use the reaction button at the bottom of your screen to raise your hand, and they'll put us in some order for questions. And we especially welcome questions from early career scientists. But right now, we're going to start out with David Marsan and then Chris Schultz. David.
Hi, thanks, Chris. Thanks, Cristiano. Very nice talk. I have one comment and one question. The comment is about the Gutenberg Richter. When it is known, when you look at a population of earthquakes, that B is equal to 1.5 separate two very different regimes. So with B, less than 1.5, the large earthquakes actually dominate the moment release. For B larger than 1.5, that's, the converse. I mean, the small events actually dominate. So, I mean, that's quite consistent with what you actually see. That's a comment. And then the question is about your swarm, behavior. So in your view, the fluid overpressure actually exists from the very beginning. So it's not like a fluid intrusion. I mean, the fluid is trapped. And I mean, did you check whether the main shock, like the Norcia earthquake, for example, actually increased, the pressure where your clusters are?
Okay, so yeah, the clusters seems to be really sensitive to main shock induced stress changes. For example, here you can see these clusters that occurred before Norcia and are located here, and this cluster turned off after Norcia. And you can see here that the stress change produced by the Norcia is negative. And so maybe this can be a reason for the turn off of this cluster C2 and C3. And so this gives us the idea or the feeling that this volume where this cluster occurs are very, very sensitive to stress changes. And on top of that, I would like to present these data from this deep borehole, showing that the overpressure, at least from this borehole, but this is the depth 3.6, 3.8. So where this cluster is occurring, it's not in the same cluster, it's about 30 kilometers north of these clusters. But here you can see that the fluid overpressure is compartmentalized. So there are pockets with fluid overpressure at different level within this 2-3 kilometers thick lithology. And so you have got heterogeneities produced by this compartmentalized fluid overpressure, plus heterogeneities due to the difference in rheology between the dolostone and the anhydrites. So you have got a volume with a